Hey, Math 30-2. Today we're going to look at permutations with repetitions. All right, looking at part 1 here. A bookstore is advertising signed copies of books about 3 famous Canadian hockey players, Gretzky, Roy, and Stevie Y. The books are arranged in a vertical display stand. One arrangement shown. Sketch all the possible arrangements. So if we call this arrangement Gretzky, Roy, and Yzerman, the next arrangement might be Gretzky, Yzerman, Roy. Then it might be Roy, Gretzky, Yzerman, Roy, Yzerman, Gretzky, and finally Yzerman, Gretzky, Roy, and Yzerman, Roy, and Gretzky. So there would be 3 factorial or 6 arrangements. So we've seen this already. Nothing really new there. However, Part B says the bookstore now sells out of the autographed Wayne Gretzky book, including the display copy, and the sales clerk replaces the Gretzky book with a second copy of the Patrick Roy book. One possible arrangement shown. Sketch the rest. Well, if these are both identical books, the 2 Roy books are identical, you can't really replace them. So you can't say Roy 1 and Roy 2, they're the same book. So the only options you have are the one listed. You could have Roy, Yzerman, Roy, and you could have Yzerman, Roy, Roy. But that is it. So now there are only 3 different arrangements. All right. So complete the following statement. The number of arrangements in B is equal to the number of arrangements in A divided by 2. Right? 6 divided by what is going to equal 3? Well, that's pretty straightforward. 6 divided by 2 is 3. Part 2, in lesson 2, we investigate the number of arrangements of all the letters in a particular word. In every case, the letters in the word were different. In this part of the investigation, we're going to see what happens if the letters repeat within the same word. So the scenario from previous, if I look at all the 4-letter permutations of the word like rose, where there are no repetitive letters in it, we notice that it is 4 perms of 4 or 24 different arrangements, or we could say 4 factorial different arrangements. And they've listed them all out there for you. Now, if we change the E in rose to an S and we get Ross, a word with 2 letters which are repeating, what happens to the number of arrangements? Well, step 1, let's complete the last column. So they've done column for column here and just changed every E into another S. So they want us to complete this last column. So instead of EORS, we're going to have SORS. And instead of EOSR, we're going to have SOSR. And so on. And instead of ESRO, SSRO. And finally, SSO. Well, there are no longer 24 different arrangements. Arrangements like Rose and ROES from the first list both become Ross in the second list. They count only as a single arrangement. So now how many different arrangements are there of Ross? Well, let's cross off any ones that appear more than once. So I've got Ross and Ross. We don't need that second one. I've got RSOS, and here's another RSOS. So those are good. I've got RSSO, and there's another RSSO. Here's one ORSS. There's another one. We don't need that one. OSRS, and here's another OSRS. Keep going. OSSR, SROS, and SROS is right there. SRSO, SRSO, SORS, that appears here. SOSR, SSRO looks good, and SSOR. So if you notice what happened, we have crossed off exactly half of the arrangements. They've been doubled up, so now there are only 12 different arrangements of ROSS. Or notice that there are half as many, or 1 divided by 2 factorial as many permutations of Ross as there are of Rose. Hence, we could say Number of permutations of Ross is 4 factorial divided by 2 factorial, which is 24 divided by 2, or 12. Let's take this a step further. If we change the O and E in rows to S, we get RSSS, a word with 3 repeating letters, and the arrangements as shown below. So again, let's complete the last column. So from up here, every O and E now become an S, so we want to change all the O's to S's. So SORS from up here now becomes SSRS, and SOSR becomes SSSR, and SSRO becomes SSRS, and finally SSOR becomes SSSR. So we've completed the last column, and again, let's see what happens. We've got to get rid of some of these repeating. So here's RSSS, those 3, 4, they're all gone. Here's SRSS, that's that one gone. SRSS, SRSS. All right, and then we've got SSRS, 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 and finally SSSR, so the ones that are SSSR are gone. So if we look, we're down to 4 different arrangements of RSSS, just those ones with the green dots beside. Notice that 1/6 of them, or 1 over 3 factorial, there's 1 over 3 factorial as many permutations of RSSS as there are of ROSE. Hence, the number of permutations of RSSS is 24 divided by 6, or we're down to 4 different arrangements. Okay. Well, let's look at this in a general statement then. If a letter appears twice in a word, we're going to divide the total number of arrangements by 2 factorial. If a letter appears 3 times in a word, we're going to divide the total number of arrangements by 3 factorial. If the letter appears 4 times in a word, we're going to divide the total number of arrangements by 4 factorial, and so on and so on. So we get this statement: the number of permutations of n objects where A are of the same type, B are of the same yet a different type, and C are the same of yet another type, and so on, can be represented by this expression: n factorial divided by A factorial, B factorial, C factorial. As many different sets of like elements, we're going to divide out in the denominator as factorials. So, find the number of permutations of the letters of the word Vancouver. Well, we add this up. There are 9 letters in the word Vancouver, so that's our n factorial. However, there are some letters doubled up. We've got 2 V's, and that's the only sets of doubles we have. Right? So 9 factorial divided by 2 factorial will give us 181400. Sorry, 440. Great. If we look at mathematical, well, we've got 2, 4, 6, 8, 12 letters in the word mathematical, and we're going to divide out all the like elements. So I notice there are 2 M's, I notice there are 3 A's, and I notice there are 2 T's, and there are no other repeated letters. So 12 factorial divided by 2 factorial, 3 factorial, 2 factorial, 2 factorial will give us, well, looks like about 19,958,400 different arrangements of the letters mathematical. Look at example 2. Brett bought a carton containing 10 mini boxes of cereal. There are 3 boxes of Corn Flakes, 2 boxes of Rice Krispies, 1 of Cocoa Pops, 1 of Shreddies, the remainder of Raisin Bran. Over a 10-day period, Brett plans to eat the contents of 1 box of cereal each morning. How many different orders are possible if on the first morning he eats a Raisin Bran? So we've got 3 Corn Flakes. We have got 2 boxes of Rice Krispies. we've got 1 Cocoa Puffs, we've got 1 Shreddies, and the rest are Raisin Bran. So that'd be 3 Raisin Bran. However, on the first morning he eats a Raisin Bran, so he no longer has 3. He's eaten that one, so he's down to 2 Raisin Bran. So the first morning's gone, he's eaten a Raisin Bran. We've only got 9 boxes left for the next 9 mornings. But we've got 3 cornflakes, so we divide out the 3 factorial for cornflakes. We've got 2 Rice Krispies, divide out 2 factorial. And we now have 2 Raisin Bran, so divide out those 2 factorial. Calculate that, and we come up with 15,120 different ways he could eat the remaining 9 boxes of cereal in 9 mornings. All right, we're going to complete this set of notes. Exploring routes using permutations and patterns. Paul and Catherine are considering the following problem. Find the number of routes from A to B if routes must always move closer. So what it means is we can't backtrack. They don't want you to go backwards. A. Paul arrived at the correct answer by tracing 10 routes on the grid. Show the different routes on the grid below. So I'd like you to try that, and then you can pause this and try it, and then you can start it up and see it again. Alright, so here are the 10 different routes. The black ones where he's starting to the right 1, or if you want to say east 1. The blue ones he goes east 2 to start. The red one he goes east 3 to start. The yellow ones he's going to go down south 1. And finally the red one was down south 2. So there are your 10 different routes. Catherine developed a quicker method. She realized that to travel from A to B involves moving 3 units east and 2 units south. And that the answer to the problem is a number of ways in which this can be done. 3 E's and 2 S's in any order. We've got the 10 orders drawn nicely above. Note that Paul's first grid shows the route east-south, east-east-south. Right? East-south, east-east-south. Solve the problem using Catherine's permutations with repetitions approach. So we know there have to be 5 blocks you gotta get to. There's 3 easts and 2 souths. That is 5. So if I call those 5 factorial ways to order those directions, but we've got like elements. We've got 3 E's. You have to go east 3 times, and you have to go south 2 times. So 5 factorial divided by 3 factorial, 2 factorial is indeed 10. So you get the same solution without having to draw them all out. Now, this method works but takes a long time. Right? It takes too long. This method works and it's really nice, but it doesn't always work. It almost always works. But this next method will work every time. So we have to learn how to do this one. This one will work every single time. Let's give it a look. The alternative approach is started below. The diagram has been rotated. There's one route from A to C. So if you look from A to C, there's one route. There's one route from A to D. There's one route from A to D. There are 2 routes from A to F. So you can go ACF or ADF. So there's the 2 routes. There are 3 routes from A to H. Right? You can go A to E to H, ACF to H, or AD through F to H. So that's why there's 3 routes there. All these numbers have been placed in the second diagram. Beautiful. How do the following answers relate? F compared to C and D. So how does F compare to C and D? Well, 2 is the same as 1 plus 1. H compared to E and F. H compared to E and F. Well, again, H is 1 plus 2. I compared to F and G. How does I compare to F and G? Well, we haven't got to G yet, but we know going along the outside, there can only be one way to get to G. And if there's 2 ways to get to F, 2 plus 1 should give us 3 routes to I. All right. So if I look at that, Use this relationship to complete the second diagram and compare your answers with Paul and Catherine's answers. So if I have 3 rows to this point going there, and I got 3 rows to this point going there, 3 plus 3 will give me 6. If I have 3 rows here going that way, and I've got 1 route only went here, and I've got 1 route coming out there, 3 plus 1 will give me 4. And 6 routes to here, 4 routes to there, 6 plus 4 will give us our final 10 routes. Now, if you recall, this looks a whole bunch like Pascal's triangle. All right. 1, 1, 1, 1, 2, 1. If I kept it going, 1, 3, 3, 1, 1, 4, 6, 4, 1, and 1, 5, 10, 10, 5, 1. So this is just using Pascal's triangle pattern by adding the 2 numbers up above, right? 3 plus 3 is 6, 6 plus 4 is 10, and so on. But the whole triangle doesn't get represented. We just need the parts that fit in the grid. So we come up with the same answer of 10, and we're really using Pascal's triangle. So that's something to remember. All right. Example 3. A supervisor of the city bus department is determining how many routes there are from the bus station to the concert hall. Again, you can't backtrack. You don't want a bus going backwards. You're going from the bus station to the concert hall. Determine the number of routes possible. The bus must always move closer to the concert hall. Always move closer. Using patterns. All right, so we're talking about Pascal's triangle here. So from here to here, there's only one way. And continuing along that route, there's only one way to get to the outside. And down to here, there's one way. And along the outside, there's still only one way all the way down. And now we can fill in the middle intersections using Pascal's triangle. One way to here, one way to here, 1 plus 1 is 2. 2 plus 1, they meet right here, which is 3. 3 and 1, they meet right here, which is 4. So 4 rows to that point. 1 route down to here and 2 to here, 1 plus 2 is 3. 3 plus 3 is 6, and 6 plus 4 is 10. And we continue going in this manner. 1 plus 3 is 4, 4 and 6 is 10, 10 and 10 is 20 to that point. 1 and 4 is 5, 5 and 10 is 15, 15 and 20 is 35. Now when we get here, we may have noticed that we're always adding the ones coming from the left and down. Well, if I look at 35, there's nothing coming down to add up with the 35. So that route of 35 must continue all the way. So there's 35 routes all the way out there. And again, there's nothing coming from this side to add to the 35 coming down. So the 35 goes down all the way. And once we get the outsides filled in, we figure out the intersection points in the middle again. So 35 here and 35 here adds up to 70. 70 and 35 is 105. 70 and 35 here is 105. And 105 and 105 gives us 210 different routes from the bus station to the concert hall. All right, so that's just simple addition. And it's the pattern developed by Pascal's triangle. How does this compare to using permutations? Let's have a quick look. I know that this box here, I have to go 3, we'll say east, and I have to go 4, 1, 2, 3, 4, south to get to the first intersection point. So if I just did that grid right there, that's 7 blocks I have to go, but I've got 3 easts which are repeating and 4 souths which are repeating. And then I look at the next block, and I notice I've got to go 2 east and 2 more south. So that's a total of 4 blocks I have to go. And I've got 2 more east and 2 more south. And this is all the same set of routes, so we're going to multiply. All right, it's not an or, it's an and we multiply with the and. So you multiply 7 factorial, 3 factorial, 4 factorial, multiplied by 4 factorial, divided by 2 factorial, 2 factorial. Try that on your calculators and you'll come up with 210. Now this method right here definitely seems simpler, right? And that's good. If you can do that, that's awesome. But this method does not always work. As in example 4. Let's have a look at example 4. A taxi company is trying to find the quickest route during rush hour traffic from the train station to the football stadium. Use patterns to determine the number of different routes that must be considered if at each intersection the taxi must always move closer to the football stadium. All right, so let's use patterns. Pascal's triangle. All right, here we go. One along the outsides, one along the outsides, only one route around the outsides, and 1 plus 1 gives us 2, 2 plus 1 is 3, and so on. 3 and 1 is 4. Well, 4 plus, there's nothing up here. Nothing to add to the 4, so the 4 continues on the outside. 1 plus 2 gives us 3. 3 and 3 is 6. 6 and 4 is 10. 10 and 4 is 14. 1 plus 3 is 4. 4 and 6 is 10. 10 and 10 is 20. 20 and 14. And so on. 1 and 4 is 5. 5 and 10. 20 and 15. 35 and 34. Right? Now, if you look at 15, there's nothing to meet the 15 that's coming down from the outside, so 15 comes straight down. Now we go 15 and 35 is 50. 50 and 69 is 119 routes from the train station to the football stadium. Explain why the permutations with repetitions formula cannot be used to determine the answer to this problem. You say, yeah, that's interesting. Why can't we? Because I had to go 1, 2, 3, 4 east. I had to go 1, 2, 3, 4, 5 south. So 4 plus 5 is 9 factorial. And I divide out the 4 east and the 5 south. If you try 9 factorial divided by 4 factorial, 5 factorial, I believe that comes out to be 126. But the answer we came up with was 119. So why doesn't it work? This doesn't work because there are holes in our grid. We've got a hole right here, and we've got this whole section that's not accounted for. So it doesn't work because there are holes in the grid. In order for our permutations with repetitions formula to work, we must have a completed grid. So if we don't know how to use Pascal's triangle, and we don't know how to do the pattern, then we can't always get the right answer. We may get it most of the time, but it doesn't always work. As soon as there are holes in the grid, we are in trouble. We need to know Pascal's triangle pattern. All right? So I'd like you to do the work in the workbook. That's it for now.